Welcome friends. Here is a question that is in the electrolysis of dipotassium succinate. The alkene gas liberated is which one? If you go for the solution, this is succinic acid, 4 carbon containing diacid is said to be succinic acid. This is known as butane-dioic acid. What is this one? This is butane-dioic acid because oic acid is a terminal functional group containing system, whereas it is consisting of two carboxylic acids. Hence it is butane-dioic acid. This butane-dioic acid is said to be succinic acid. The other name of butane-dioic acid is succinic acid. Whenever this is allowed to react with potassium hydroxide, that is acid and base reaction takes place. This is base, this is acid. This acid, whenever allowed to react with the base, neutralization occurs. As a result of neutralization, water followed by salt formation takes place. This is the salt. This is the salt. This is known as potassium succinate. This is known as what? Potassium succinate. We can say it as potassium succinate. With this potassium succinate, aqueous solution of potassium succinate is electrolyzed. As a result, which alkene gas is liberated? Our question is, when potassium succinate is electrolyzed, aqueous solution of potassium succinate is electrolyzed. As a result, which alkene at which electrode is going to be liberated? The given solution is aqueous solution of potassium succinate. It is consisting cations H plus followed by K plus, as well as anions, succinate anion. This is succinate anion followed by OH minus. These are the ions present in competition. Whereas these of all are cations. Cations undergoes reduction. Reduction takes place at the anode, at the cathode. So at the cathode, these two are competitors. And at the anode, these two are competitors to undergo oxidation and to undergo reduction. As a result, here the discharge potential of hydrogen is little. Hence, hydrogen gas is going to be liberated. Whereas, compared to the OH minus discharge potential, potassium succinate discharge potential is little. Hence, this potassium succinate is preferable. This undergoes oxidation. Oxidation is a process. It participates in losing of electrons. Whenever it participates in losing of electrons, it is converted as radical. It is converted as what? Radical by losing 2 electrons. This process is known as oxidation. After this, to become very much stable, it also loses carbon dioxide molecule homolytical cleavage, results into the formation of what? Diradical of ethylene. It undergoes dimerization. As a result, that is ethylene formation takes place. So therefore, at the cathode, hydrogen gas liberates, and at the anode, ethylene gas is going to be liberated. Hence, the gas that is going to be liberated, at the anode on electrolysis of potassium succinate is ethylene is the gas. Ethylene is the gas. Along with the ethylene gas, the spectator cation K plus present in the solution, and the spectator anion OH minus is also present in the solution, that it is KOH. KOH is what? Base. As the base concentration increases, the pH of the solution as reaction proceeds also what? Increases. The spectator cation and the spectator anions K plus followed by OH minus concentrations goes on increasing. These two combination is a base. OH minus concentration goes on increasing. Hence, the pH of the solution is also goes on increasing. And another question present in the previous, that is in presence of peroxides, that is radical initiators. If I go for addition of HCl and the addition of HI, they does not provides any kind of anti-Markovnik of addition product. What might be the reason behind not producing of anti-Markovnik of products when either HCl and HI is added to the double bond system? Suppose in presence of peroxides, generally what happens is, this is peroxide. This peroxide in presence of HNu or the photochemical condition or the heating conditions, radicals are going to be generated, that is alkoxy radical is generated. This is a radical. This is initiator. Whereas this radical, whenever allowed to react with the hydrogen halide, what happens is, it results into the formation of a stable ROH followed by X radical formation takes place. This X radical, whenever it is added to the alkene system, it results into the formation of stablest free radical. This stablest generated free radical further combines with another molecule of the HX and results into the formation of what? Anti-Marconic of addition of HX to the alkene system in this manner. And this particular way is possible if the process is spontaneous, that is delta G of these two steps is negative, then that reaction will becomes what? Spontaneous process. Whereas only for HBr, if this is Br, only for HBr, a sum of these two reactions related delta G will becomes negative. So therefore, it works for the HBr. Whereas if I take HCl as well as HI, out of these two steps, one in them is exothermic and other in them is endothermic. Overall summation of delta G of these two steps will becomes positive. Hence, reaction with respect to HCl, reaction with respect to HI does not works. So therefore, this particular anti-Marconic of addition product formation is not possible whenever addition occurs either with respect to HCl or with respect to what? HI conditions. Once again, if I conclude, these two steps are the deciding steps to decide the whether the reaction is occurring or not occurring. If you say technically, the delta G of the process is sum of the delta G's involved in step 1 followed by step 2. In case of HBr addition, sum of the delta G's of these two becomes negative, hence it becomes spontaneous. Such of product formation takes place. This product is anti-Marconic of product. This is anti-Marconic of product. Whereas if I take either HCl or HI, one in them is exothermic, one in them is endothermic. Overall, the delta G of these two steps is positive, implies non-spontaneous. As being it is non-spontaneous, it does not occur, it doesn't results into anti-Marconic of product formation. Thus, it just works for the HBr, not for the HCl followed by what? HI. In the addition of HI in presence of peroxide, catalyst does not offers the anti-Marconic of product. What might be the reason behind non-forming of anti-Marconic of product for the HI addition to the alkene system? Suppose this is my alkene system. In presence of peroxide initiators like peracids, otherwise peroxy radicals, in presence of H nu conditions, if I add HI, it always results which particular product? Marconic of addition product only takes place, but it doesn't gives anti-Marconic of addition products like this. This doesn't comes, only this will comes. What might be the reason behind not getting of anti-Marconic of product when HI is added to the alkenes, unsymmetrical alkenes in presence of peroxides, that is in presence of radical initiators. Here there are two specific ways to say the reason. Number one is, suppose to this addition related previously explained out of two steps, one in them is exothermic, other in them is endothermic. Endothermic dominates, delta G becomes positive, so it becomes non-spontaneous, it does not occur. And in another way to say more properly, this is one with respect to delta G version. Other is whatever we are expecting this I radical generated, suppose this I addition across the double bond is not possible. Whatever double bond is there, double bond on reaction with I result into the formation of stablest radical in which alkene is connected with the I formation is a non-spontaneous part. It doesn't have that kind of strength that it can make a spontaneous addition over the double bond, because this particular step will becomes endothermic step. That is this one. It is not deciding one. It is requires more amount of driving force that we have to supply from the outside, which is non-spontaneous on its own. To make it spontaneous, we have to supply a lot. That is not possible. Hence, this particular addition is as being non-spontaneous. Addition of hydrogen iodide over the double bond in presence of peroxide to generate anti-Marconic of product becomes not possible. Becomes not possible. Thus, we can conclude that the reason what we said, because of iodine atom is not reactive enough to add across the double bond to make the iodine connected alkene radical as the intermediate is not possible because of lower reactivity of the iodine. Thus, it doesn't result anti-Marconic of product. Yes, there is an alkene A that is undergoing ozonolysis. On reductive ozonolysis, it is producing two carbonyl compounds. One is acetone and second one is propanaldehyde. One is acetone followed by propanaldehyde. Acetone is internal carbonyl compound as we know, and propanaldehyde is terminal carbonyl compound. Acetone is this one. This is known as what? Acetone, and this is propanaldehyde. One is acetone followed by another one is propanaldehyde. Both are produced in 1:1 ratio. You are asked to write the starting material alkene which undergoes ozonolysis results this acetone as well as propanaldehyde in 1:1 ratio. If I write these two structures very close, that is, this is the structure. This is propanaldehyde followed by acetone. In ozonolysis, whatever the carbonyls are generated, these are coming as a result of what? Double bond. This is originally a double bond system. If this double bond is broken, having carbonyls generated terminal and internal carbonyls combination comes out. Hence, the starting material that can result this particular acetone followed by propanaldehyde is this one. Hence, the name of the compound is this is 1, 2, 3, 4, 5. That is 2-methyl pent-2-ene. What is its name? 2-methyl pent-2-ene is the name of the compound. 2-methyl pent-2-ene is my alkene, whereas this alkene undergoes ozonolysis under reduction conditions. Reductive ozonolysis results. One is this is resulted into internal carbonyl system because it doesn't have any kind of hydrogens. It is having hydrogen, hence it is resulted into terminal carbonyl system with 3 carbons is propanaldehyde. 3 carbons internal will becomes what? Acetone, that is propan-2-1 followed by propanaldehyde formation occurs from 2-methyl pent-2-ene system. A question from the previous, that is the reagent used for the conversion of but-1-ene to butane is but-1-ene is like this. This is but-1-ene. This but-1-ene is expected to be converted to butane, that is whatever unsaturation of terminal is there, that terminal has to be converted to saturated situation. For that, what are the suitable reagents? And the list of reagents provided for us are Sn followed by HCl, zinc followed by Hg, zinc followed by ZnHg followed by HCl. It should be required something Sunday. And zinc followed by HCl, palladium followed by HCl, zinc followed by HCl, palladium followed by hydrogen. Whereas except these of all are huge sources of hydrogen. In short time, within less time, excess quantity of hydrogen is going to be liberated. Sn followed by HCl, zinc followed by HCl, ZnHg followed by HCl. These are generally used for conversion of other functional groups other than unsaturations, whatever are there. Other than unsaturations containing, other than normal unsaturations containing unsaturated functional groups like carbonyl functional groups and other functional groups to convert to some other lower oxidation number functional groups, we will take the help of Sn followed by HCl, zinc followed by HCl, Clemmensen reduction conditions, that is carbonyl compounds to corresponding primary and the secondary alcohols purpose, we will take the help of ZnHg followed by HCl, because these of all are huge source of hydrogen and is available for the short time. Whereas in order to reduce these unsaturations like homo-unsaturations, double bond related, triple bond related systems to saturated systems, we required a huge quantity of the hydrogen for a huge amount of time. That is, for long time we required a continuous supply of hydrogen, and that is possible if I take palladium followed by excess quantity of hydrogen which can sustain for lengthy of times. In that conditions only these unsaturations are generally converted into saturated compound. Hence, the best suitable reagent for the conversion of homo-unsaturations like carbon-carbon double bonds and carbon-carbon triple bonds to carbon-carbon single bond system is either Sabatier-Sunderens reaction, that is nickel followed by hydrogen, ranionickel followed by hydrogen, palladium followed by hydrogen, or platinum followed by hydrogen. These conditions are suitable instead of metal followed by acid, metal alloys followed by acids like Sn followed by HCl, zinc followed by HCl, zinc amalgam followed by HCl. Instead of this metal supported followed by a huge pressure of hydrogen which can sustain for lengthy hours together is best reagent. Hence palladium followed by hydrogen is the best reagent for the conversion of homo unsaturations to saturated systems.